In the previous two lectures in tensor analysis, we have discussed the fundamental contravariant tensor and the covariant fundamental tensor. Now we will see the application of these fundamental tensors. You will see that when we take the inner product of a given tensor with these fundamental tensors, then we get a new tensor, and that very new tensor is known as associated tensor. And in fact, this associated tensor is obtained by a process which is performed by the help of these contravariant fundamental tensor and the covariant fundamental tensor, and that process is called raising and lowering of indices. So what is this these processes, raising and lowering of indices, and how these processes are performed with the help of the contravariant fundamental tensor and the covariant fundamental tensor, we will see first of all in this lecture. In fact, there will be two parts of this lecture. In first part, we will see how the associated tensors are obtained by the process raising and lowering of indices. And then we will see a very important fact that the two processes, that is raising and lowering of indices, are actually reciprocal to each other. We will also see the proof of this very important statement. In fact, as I have told you, that the operation of raising of indices and the lowering of indices, these both operations are performed with the help of fundamental tensors. If you want to perform the process of raising of indices, then that is done with the help of contravariant fundamental tensor Gij, that is G super Ij. And similarly, if your aim is to done the operation of lowering of indices, that can be performed with the help of the covariant fundamental tensor G sub Ij. I hope you have understand this statement. Actually, you know, whenever the suffix will be raised, then a covariant index will change into a contravariant index, because the superscript is known as a contravariant index and the subscript is known as the covariant index. So by raising a suffix, a covariant index will be changed into a contravariant index, and similarly by lowering a suffix, a contravariant index will be changed into a covariant index. And as I have told you earlier, that these operations is performed by taking the inner multiplication of the fundamental tensors G super Ij and G sub Ij with the given tensor. But how it will be done, we will see here. And as I have told you earlier, that after these operations, raising and lowering of indices, that is by taking the inner multiplication of the given tensor with these fundamental tensors, that is G super Ij and G sub Ij, we get a new tensor, and that very new tensor is called associated tensor. So in nutshell, you can define this associated tensor in this manner, as I have written here for your convenience, that the tensor obtained as a result of raising and lowering operation with fundamental tensors is called associated tensor. And this operation will be performed by taking the inner multiplication of the fundamental tensors G super Ij and G sub Ij with the given tensor. Now, in fact, we will explain in a quantitative manner by calculation all of these facts. So, first of all, we consider the ranging of a suffix. Ranging of a suffix. How this operation is defined, let us see. Ranging of a suffix. In fact, ranging of a suffix can be defined for a covariant tensor, because in covariant tensor there is subscript and we have to range that subscript into the superscript. So whenever you talk about the ranging of a suffix, you have to consider a covariant tensor, not contravariant tensor. So first of all, we will define this operation for a covariant tensor of first rank, and then we will generalize that definition. Let us see. So let A sub j is a covariant tensor of rank 1, or you may also call it a covariant vector or a covariant vector. In fact, if you want to range this subscript j, then what we have to do? Actually, as I have told you earlier, this is done with the help of the fundamental tensors. So if you want to raise the suffix of a covariant tensor of rank 1, you have to take the inner multiplication of this given tensor A sub j with the contravariant fundamental tensor Gij. So you can define then the operation of raising of suffix for this tensor A sub j is defined as. How we will define it? Let us take the inner multiplication of this given tensor with the contravariant fundamental tensor. You know, G super Ij is our contravariant fundamental tensor, and we take the inner multiplication of this Gij with the given tensor A sub j. And after taking this multiplication, the result will be simply A super I. A super I. Let us say this equation 1. Just as a technique, let us see here. Since j is once as a superscript and once as a subscript, then remember, when you will take the inner product of this A sub j with the G super ij, then you have to drop this j and you simply get A super I. Later on, we will show that this A super I is a tensor, and in fact this A super I is nothing, this is an associated tensor. We will prove later on. So this A super I is known as an associated tensor. Associated tensor. So this equation 1 defines the raising of a suffix operation with the help of this contravariant fundamental tensor for a covariant tensor of rank 1, or you can say a covariant vector. Now we will generalize this definition. When you generalize this definition, you have to consider a tensor of higher rank. So now consider a tensor of higher rank. Say, let us say this tensor is a super L mj. Let us say this is actually a mixed tensor of rank 3, and you can take any tensor of any rank. In fact, in this condition, if you want to define this operation of raising of suffix, then again we will take the inner product of this given tensor A super L sub mj with the contravariant fundamental tensor G super ij. So G super ij multiplied with A super L mj, and you can see here actually j is the repeated index. It is once as a superscript and once as a subscript. So the technique which you have learnt just now, you can write that this will be a tensor A super IL sub m. And again this tensor A super IL sub m, this will be an associated tensor. This is called an associated tensor. Now we will see the operation of lowering of a suffix. So next you have to consider lowering of the suffix. Number 2, lowering of suffix. In fact, as you have defined the raising of suffix, first of all in case of a covariant tensor of rank 1, and then you have generalized that definition. Similarly, one thing you should remember here, if you want to perform the operation of lowering of a suffix, then you have to consider, if you consider the first rank tensor, then you must consider in fact a contravariant tensor, because contravariant tensor of first rank will have one superscript and that should be lowered, and so we must consider a contravariant tensor of first rank in this case. So consider a contravariant tensor of rank 1, or you may also call it a contravariant vector. Let us say this contravariant tensor of rank 1 is A super j. Then if you want to lower this subscript j, then what we have to do? In this case, actually we will take the inner product of this given tensor A super j with the covariant fundamental tensor Gij. Then G sub ij A super J, and this is defined as AJ, AJ, and say this is equation 3. You can see same technique. Here J is once as a subscript and once as a superscript, so I have dropped it, and the result is a covariant tensor of rank 1, and in fact this resulting tensor A sub J is actually known as what? This is known, sorry, this will be not A sub J but A sub I. J is common, so this will be A sub I. Sub I. Yes, this will be A sub I. And as I have told you that this tensor A sub I will be called an associated tensor. Associated tensor. In fact, in this equation 3, you have defined the lowering of suffix in case of a contravariant tensor of rank 1. And now you can generalize this definition for a tensor of any higher rank. So if you want to generalize this definition, let us consider another tensor of higher rank. So let us consider a tensor of higher rank. Let us say this tensor is A LJ M, super LJ sub M. Then if you want to perform the operation of lowering of suffix, you have again to take the inner product of this given tensor with the covariant fundamental tensor. Then we will take the product of G sub ij with this given tensor. This is A LJM. Now see, this resulting tensor will be what? You can see this will be L. J is the repeated index, so we will drop it, and this will be A super L IM. A super L. And this is equation 4. Again, since this tensor A super L sub IM has been obtained after the inner multiplication of this given tensor A super LJ sub M with the covariant fundamental tensor, so according to the definition, actually this resulting tensor is what? This is associated tensor. Associated tensor. Actually, in accordance with the definition, I have told that these resulting tensors are associated tensor. But you can prove that after the operation of lowering of suffix and raising of suffix, we get a tensor. This result can be proved. It means you can show that these quantities, that is A super I, or you can say this A super IL sub M or A sub I, all these are tensors. You can prove it. How we will prove it? You know, In fact, whenever we have to show that a given quantity is a tensor, we must remember that any tensor is defined by a transformation law. So we will see these quantities obey the law of transformation of tensor or not. And actually that transformation law will prove that these resulting quantities are tensors or not tensors. And for this, let us consider this first equation, for example, this equation 1. In fact, here no prime have been used. It means you are talking about an unprimed coordinate system. Now let us consider a prime coordinate system and write this equation 1 in that primed coordinate system. So let us consider to prove that we get tensors after lowering and raising of suffix. Lowering and raising of suffix. We have to prove actually this important fact. It means you have to show that after the inner multiplication of a given tensor with the fundamental tensor, the result is again a tensor. We have to show. And for this, you can take any, you can consider any equation through 1 to 4. So let us consider that we have to write equation 1 in a coordinate system where the independent variables are x prime mu. So in a system of variables, say x prime mu, equation 1 is written as, see the equation 1. You want to write this equation 1 in a prime coordinate system. So how we will write, you know, you have studied these things in the previous lectures. You can write this in this manner. G super mu nu, subscript has been changed, times A prime nu, and this is equal to A prime mu. You can see now we have considered that our fundamental tensor is G super mu nu and the given tensor is A prime sub nu. Then according to the definition of the raising of suffix, this nu will be omitted and we get A prime mu. Now we have to show that this quantity A super I is a tensor. You have to show this. And for this, we will follow actually the transformation law. You can see, we can write this equation in this way. This is A prime mu. In fact, this quantity in RHS has been written in LHS now. Now, this fundamental tensor, G super mu nu, according to the transformation law followed by this contravariant fundamental tensor, you know, you have studied in the previous lecture that this fundamental tensor is actually a contravariant tensor of second rank. So it will follow the transformation law of a fundament transformation law of a second rank tensor. And here we should also put here prime, G prime. So according to the transformation law of a second rank contravariant tensor, what you can write for this G prime mu nu? You can see we can write it. This will be, let us say, Gij, super ij, and then there will be del x prime mu by del xi times del x prime nu by del xj. Sorry, del xj, you know. This is in accordance with the transformation law followed by a contravariant tensor of second rank. And again, according to the transformation law of a first rank covariant tensor, what is this A prime nu? A prime nu is actually a covariant tensor of first rank in the primed coordinate system. So according to the transformation law of a covariant tensor of first rank, what we can write for this A prime nu? If the components of this tensor in the unprimed coordinate system is, let us say, AL, then we will write AL times del XL over del X prime nu. Del X prime nu. Del X prime nu. We can write. I hope you remember this transformation law because you have studied these things in very detail in the earlier lectures. Now let us simplify the RHS of this equation. You can see A prime mu. This will be equal to. Now let us write these partial derivatives first of all. This will be del x prime mu by del xi times del x prime mu by del xj. So this is del this equal to, there is some problem here. Let us see. This equal to del x prime mu by del xi times del x prime nu by del xj times del xl by del x prime nu, and the remaining factors are G super ij times AL. This is G super ij times AL. Now see, in fact this del x prime nu and this del x prime nu both will cancel out, and your result is del x prime mu by del xi and times del xl by del xj and G super ij AL. Now can you recognize what is this? This you should definitely recognize it because you have studied this thing in previous lecture. This is nothing, this is simply the Kronecker delta Lj. Kronecker delta L. This is just definition of Kronecker delta which we have learnt in the introductory lecture on tensor analysis. So this is del x prime mu by del xi times Kronecker delta Lj Al. Now see, if this L is equal to J, then your Kronecker delta Lj is equal to 1. And if L is not equal to J, then this Kronecker delta Lj is equal to 0. So to get the non-zero value, we must put this J equal to L. So you can see this will be equal to del x prime mu by del xi and delta this is delta Jj. Actually, I have replaced this L by J, and so this will be Aj. But this Kronecker delta, as you can see here, when L is equal to J, this will be 1. And so if it is 1, then we get A prime mu is equal to A sub J. A prime mu is equal to in fact Gij. I have dropped actually this Gij. There is also G super Ij. Remember it. There is G super Ij. Now this A prime mu will be equal to Aj times G super Ij and del x prime mu by del xi. Now see this product. Here this covariant vector or covariant tensor of rank 1 A sub j has been multiplied with this contravariant fundamental tensor Gij. So according to the definition of, you can see here, according to the definition of raising of suffix, what you can write it? You can see this J will be omitted and this will be simply equal to A super I, and this is del x prime mu by del xi. In fact, here I have used the definition of the raising of suffix. You can see here G super ij times aj is equal to A super I. This equation 1 has been used here. And so this A prime mu super mu is equal to this much. Now see this equation. When you look into this equation seriously, you can easily say, what is this? This equation actually refers that this quantity A super I transforms just like a contravariant tensor of rank 1. So definitely you can say that this A super I is nothing, it is a tensor. So you can easily say that this equation shows that AI transforms like a contravariant tensor of rank 1, and so A super I is a contravariant tensor of rank 1. So this equation implies A super I is a contravariant tensor of rank 1. So you can see, I have told you that whenever you take the inner product of a fundamental tensor with a given tensor, then the resulting quantity is also a tensor. So we have proved it that this type of product always gives a tensor, and that resulting tensor is known as associated tensor. So I hope you have understand how associated tensor is obtained. In fact, in the end of the lecture, I will just mark it that if you want to get a associated tensor, you have to take associated tensor means is a tensor associated with any given tensor. So if a tensor is given and you have to find a tensor associated with that, then you have to take the inner product of the given tensor with the fundamental tensor, and that fundamental tensor may be a contravariant fundamental tensor or a covariant in accordance with the nature of the given tensor. So this is the first part of this lecture. Now in second part of this lecture, we will see a very important fact, or we will actually explain or prove a very important fact, and that is what? That fact is that the processes of raising of suffix and lowering of suffix is actually reciprocal to each other. When you say that the two processes of raising and lowering of indices are reciprocal to each other, what does it mean? It means if the index is first raised and then lowered, or vice versa, it means the index is first lowered and then raised, then you always get the original tensor. And that's why we say that the process of raising and lowering of indices are reciprocal to each other. So now we will actually prove this fact in a quantitative manner. So this is a very remarkable fact that the two processes of raising and lowering of indices are reciprocal to each other. Reciprocal to each other. Reciprocal to each other. And we have to show this statement. I want to prove this statement. And what is the meaning of this statement? As I have told you just now, that when you say that the raising and lowering of indices are reciprocal to each other, it means if the index is first raised and then lowered, or the index is first lowered and then raised, then you get the original tensor. So we will now prove this very important fact. And to prove this, let us consider a mixed tensor. For a general result, we consider not a covariant tensor or contravariant tensor of first rank, but we consider a mixed tensor of any higher rank. Let us consider. So we want to prove this very important fact. And for this, let us consider a tensor let us say A sub ij super L. Let us consider. Now, first of all, let us raise the index this j, index j, by taking the inner product with the contravariant fundamental tensor, let us say pj. So now we take the inner product of the fundamental tensor, let us say pj, with this given tensor A super L sub ij. And what will be the result? You can easily say j is the common indices, so we will drop it and our result will be A super PL sub I. Again there is some problem. Super PL sub I. And say this is your equation 6. So here actually we have raised the indices j. Now we will take the lowering operation of the index, let us say p, and that can be performed by taking its inner product with the covariant fundamental tensor, let us say g sub mp. So again lowering the index p by taking its inner product with covariant fundamental tensor, let us say g sub mp. We get what we will get. You can see this is g sub mp multiplied by a this PLI. Now what will be the result? P will be omitted. You can see this will be A L M I or I M. MI or IM. And say this is your equation 7. Now you can see that this tensor A super L I M is same as is same as that of the tensor A super Lij. Super L sub ij. This tensor, you can see this tensor and this tensor are same. Don't confuse with the index m here instead of j, but we can say that these two tensors are identical, or you can say these two tensors are exactly same. indices, this index m may be freely changed. You can write here j instead of m because this is in fact not a repeated index. this is this index has not any special significance that can be replaced by j. So in this way, what you have seen what you see here, you see that when we perform the operation of raising of index on a given tensor, then the resulting tensor we have obtained is like A super PL sub I, and when the operation of lowering of index is performed on this resulting tensor, then we get again the same tensor which we have started from here. It means you can say if on a given tensor, first of all, the operation of raising of index is performed, and after that, after that you get a tensor, and if you perform the lowering of index operation on the obtained tensor, then you get the original tensor. It means for simplicity, let us say by the operation of raising of index on tensor A, you get a tensor B, let us say. It means raising index operation is performed on A and you get B. And when lowering index operation is performed on B, then you again get A. This is the meaning. And that's why we simply say that the two processes of raising and lowering of indices are reciprocal to each other. And as I have told you, it means if the index is first raised and then lowered, or first lowered or then raised, then we get the original tensor. So I hope you have understand this very important fact. So this is the concept of the associated tensor. In nutshell, as a summary, you can say that whenever the process of raising of a suffix or lowering of a suffix is performed on a given tensor by taking the inner multiplication of the given tensor with the fundamental contravariant tensor or covariant tensor, then the resulting tensor obtained is called associated tensor. And these two processes are reciprocal of one another. So in this lecture, we have discussed associated tensor, and after this concept, in the next lecture, we will see some of the important problems related to the metric tensor.